So in this section, I'm going to talk about some optimization for Hough transform. Uh, it's not that important, but if you're already here, might as well know it. So one of the things that we talked about is that we can take advantage of the gradient information that's provided from the edge operator. So when an edge operator provides me the gradient information, then that essentially tells me the theta, the angle of which the gradient goes. So that gives me information on the theta. So that means that I do not have to calculate 360 lines. I can simply calculate the line that corresponds to that theta, because I already know the theta from the gradient values that I calculated. So that could save a lot of time. The problem with that is when you have error in the image, then then the lines might not intersect. So suppose there is a line, but there's error in the image, and these points are not on top of each other. So then you have no way of knowing if there's actually a line or not because of this error. So what you could do, as we mentioned earlier, is you could use a little cluster region and say, oh, if these points are around this region, then there must be a line there. That is one way to do it, but you're going to get into the regions intersecting problem again. So that is the problem with using the gradient information. There's probably a smarter approach of simply calculating the value that's around the gradient. So suppose if the gradient that you got was 60 degrees, then you can calculate simply from 45 degrees to 90 degrees, or 50 degrees to 70 degrees, so that the 60 degrees is within the range of 50 degrees to 70 degrees. So that way you don't have to do the calculation of all 360 degrees. So you would reduce the constant on the in front of the running time. So instead of 360 as the constant on the top, you would probably end up with 20 or 30. And that would improve the running time by quite a bit. That is one of the optimizations that we could do to the Hough transform. And we also went over the errors. We went over the theory of how Hough transform works. The part I skipped was a line represented in y equals to mx plus c space. So instead of using rho and theta, a lot of textbooks mentioned actually using m as the intercept, m as the slope, and c as the intercept. So using the MC space as opposed to the rho and theta space. I find that that might not be as relevant if you already understand how polar coordinates work. And that has the issue with an infinite space, because if a line is vertical, then m is infinite. So that is the reason that most people don't use the MC space. It is quite interesting how you can transform a line into a point and a point into a line. So the MC space and the XY coordinate space are duals of each other. That is pretty interesting, but that's not something that I've gone through. So that's it for all we have so far. The next section will be on Hough circles and how we detect circles using Hough transformation. And after that, we're going to generalize Hough transform to detect any shape that we want.